Alright, today we are going to look at Chapter 23, which is Magnetic Flux and Faraday's Law of Induction, and we're going to look at problems 14, 19, 30, and 33. So first off, number 14 says we have a loop of wire with a certain area and a resistance, and perpendicular to the plane of the loop we have a magnetic field, and at what rate must this magnetic field change in order to induce a certain amount of current? So I'm going to start here because we got a lot of numbers with just listing our givens. So it says the area of the loop is 7.4 times 10 to the negative second meters squared. The resistance in the loop is 110 ohms. The magnetic field is 0.28 Tesla. And the induced current is 0.32 amps. Now, step number one is going to be to find the induced voltage from the induced current and the resistance. So we are going to use Ohm's law and do V equals IR. And so if you multiply 0.32 times 110, you get the induced voltage to be 35.2 volts. Step 2 then will be to use the equation that relates induced voltage to your change in flux, which says that the induced voltage is negative, and you can kind of just say the absolute value of the change in flux over the change in time, which is going to be equal to your change in the magnetic field times the area times the cosine of theta divided by time. The cosine of theta can just drop out in this case since the magnetic field is parallel to the plane of the loop. And what's unique about this problem is they're actually asking us to find the magnetic field per time. So they want us to find what is delta B over T. And if you rearrange stuff a little bit, hopefully you can see delta B over delta T is your induced voltage divided by the area. And so you get 35.2 divided by 7.4 times 10 to the negative second. And that will give you an answer of 475.7. And your units will be Teslas per second. Next one is number 19. And number 19 shows a picture of a magnet that's kind of situated like this here with a south pole and a north pole. And along the magnet's axis is a ring. And they want to know if the ring is dropped and falling in between the poles of the magnet, whether the induced current is clockwise or counterclockwise. In part A here. So first thing you've got to think about, oh, and I have the poles drawn opposite, sorry here. That is a north pole and that is a south pole in the picture. So first thing you have to think about is the direction of the magnetic field between the poles of the loop, and magnetic field lines will always point from north to south, so I'm just going to draw that in there. And next you've got to think about which way you want your current to go in the loop. So as the loop drops, you're going to be adding more magnetic field or more flux through the loop in that kind of right downward direction, how I have it drawn here. And so what Mother Nature wants to do is create a field opposite that. So that means that your current has to, if you take your right hand rule and you put your thumb down into the page and your fingers have to kind of curl clockwise, that would create a current that's going to induce a magnetic field opposite that. So for part A, you would want a clockwise current that would go something like this. Again, the reason for that is if you use your right hand rule with your fingers curling clockwise, your thumb will kind of point into the page in the left, which will oppose this increasing magnetic field when you are moving the ring down. Part B then wants to know if the loop is being lowered below the magnet. The opposite is actually going to happen when it's below the magnet here, is the magnetic field lines going from north to south going through the loop is actually going to start decreasing, and so Mother Nature wants to counteract that by increasing the magnetic field lines going down and to the right. And she does that by inducing a counterclockwise current, so sort of like this direction here. So then when you take your right-hand rule, your fingers curl in the direction of the current, your thumb kind of points out of the page, and if you think of this as kind of like a three-dimensional picture, your thumb will be pointing in the direction of this magnetic field from the North Pole to the South Pole. All right, next one is problem 30. And what 30 is asking is it gives a picture of a magnetic field coming out of the page with a resistor and a rod that is able to move to the right with a certain velocity. And they want to know in A, the speed in which the bar would need to move in order to produce a current of 0.125 amps in the resistor. So again, I'm just going to go ahead and list my givens. The length of my rod is 0.45 meters. The resistance in the circuit is 12.5 ohms. And the magnetic field that they have is 0.750 Teslas out of the page. And so in part A, your induced current is 0.125 amps. So that is your other given here. And first thing we need to do is find your induced voltage, which you can use V equals I times R. And so you're going to get 0.125 times the resistance of 12.5 and get 1.5625 volts. And then from there, you can relate this induced voltage, 1.5625, to the absolute value of your change in flux over the change in time. And we know from simplifying things down that this is equal to B times L times V. The magnetic field times the length of the rod times its speed. So plugging in your values, we will get 1.5625 equals 0.75 times 0.45, the length, times the velocity. And you can solve for the velocity of the rod to be 4.63 meters per second. And then in part B, they want us to look at how would your answer to part A change if the bar was moving to the left instead of the right. And your answer would not change at all. And the reason for this is that this equation right here is independent of the direction of the bar's motion. So it would be exactly the same. The bar would just be moving the opposite way. And so then the last one we are going to look at is number 33. And number 33 says, suppose the mechanical power delivered to the rod in example 23-3 is 7.9 watts. And then we want to find the current and the speed of the rod. So first thing you have to do is go to example problem 23-3, which is, let me find it here. It starts on page 779 of your book. And what it shows is a light bulb and a rod that can move freely to the left and to the right here. And so I'll kind of draw a picture of what we've got. We've got a light bulb, so I'm going to label that R with a resistance. We've got your rod right here. And they label the length of the rod L there. And it is moving to the left here. So they're saying, and I'm going to just list our givens from the active example that they had. The resistance was 12 ohms. The length was 1.25 meters. The B field that they solved for in that problem, if you look through that active example, was 2 Teslas. The velocity is 3.1 meters per second left. And then finally, the power is 7.9 watts, and that is what the new part of your problem here is saying, if the power is 7.9 watts. So in part A, we want to find the power, that, or I guess the induced current if the power is 7.9 watts. And so we will go ahead and use P equals IV, which is the same thing as I squared times R. And you can go ahead and get, 7.9 equals I squared times 12. And you can solve for I to be 0.81 amps. Then in part B, they want us to find the speed of the rod based on this. And so the key idea for this is that the power in the electrical circuit, which was what we kind of looked at in part A, is the same power that mechanical power that you must deliver in order to move the rod. And so that power is going to be equal to force times velocity, way back when in the fall when we studied that. And the force, you've got to think, we've got current going through this rod, and it has a certain length. So we're going to use force equals Bill sine theta. So we're going to get BIL times the velocity. And we will have 7.9 equals the magnetic field of 2 times the currents from above of 0.81 times the length of the rod, 1.25 meters, times the velocity. And you can solve for the velocity to be 3.9 meters per second in this case here.